Hi, everyone. I'm Sabbir, and this is Erika. We are from Northeastern University. So here we are to present our paper that is already mentioned. So let's start. So in this paper, we propose a new methodology for player modeling, and we call it Interactive Behavior Analytics Method, or in short, IBA. This method facilitates knowledge discovery from game data using human experts for context-aware analysis. In this presentation, we'll first describe the methodology and then demonstrate the use of the methodology using a case study. So now we move into the details of the IBA methodology. So here you can see a diagram that shows the overall methodology of IBA. On the high-level overview, this methodology is comprised of two visualization systems, a labeling mechanism, and some abstraction algorithms. So the first step here is to format the game data to feed into a visualization system, which is called StratMapper. So StratMapper is a visualization system and labeling mechanism for game data. At the center of the application, you can see a two-dimensional game map. Here it is shown for DotA. You can zoom in and out. Below it is a timeline, which you can also zoom in and out, visualizing all the events in the games. A tooltip appears here with detailed information upon hovering over the game icons. The timeline allows users to select a temporal period of interest. You can move around to filter events and users on the game map and display only those that appear during those selected time period. So in summary, this visualization helps users to visualize the game as a whole and to identify player activities and strategies. So StratMapper visualization is used to label strategic complex events using the labeling mechanism. So these labels are decided by human experts. So now we come to the point how the labels are decided. So developing labels are similar to developing codes for qualitative thematic analysis. First, the members of the research team familiarize themselves with the game to be labeled. Once the researchers are familiar and comfortable with the game space, they discuss the types of strategic actions and actions taken during gameplay to identify recurring patterns and themes within the game. From there, they then identify a set of labels for decision-making, strategic and tactical behaviors. So once the labels are identified, team members can individually label the game using StratMapper. So as we have already mentioned, StratMapper has a labeling mechanism. In this slide, we show a test label. So this is done by selecting a particular time period in the timeline and muting irrelevant units and events in the game, and then adding the label names and other relative information. So here the test label appears, you can see. So there we show two other labels, that is team, fight, and farm, that we have used in this research. So after the labeling is done, the label data is then processed and feed into another visualization system that is named Glyph. So Glyph is a visualization system that allows easy understanding as well as investigation of player strategies. So Glyph is comprised of three visual representations: a state graph, a sequence graph, and a group graph. In the state graph, the states are the game states, and they are represented as nodes, and the transition as links. In the sequence graph, each node represents a full sequence of state actions for a player. You can select a node, and then you can see the sequences in the state graph and the complete sequence of states below the state graph. Similarly, upon selecting a node in the group graph, you can see the players in the group and also the team behavior in the state graph. So one thing to note here is that the distance between the sequence nodes in the sequence graph shows how similar the sequences are for the players. So this glyph is used to extract and analyze the gameplay strategies, which we will discuss later. Sometimes the resulting patterns may be incomprehensible or the labels may be incomplete, and as a result, the team may discuss their interpretations of labels and they can revise the labels accordingly. So as a result, this becomes an iterative process, and that is the main idea behind the IBA methodology. So the next phase of our presentation is actually focusing on the analysis from glyph visualization, and Erica will lead that.
So to demonstrate how IBA can be used to analyze and understand game data, we're going to go over one of the case studies we did that we talk about in the paper. We talk about 2 case studies in the paper, and we go into much more detail there, but unfortunately due to time, I'm just going to give like a very high-level example from one of them, which used the game Defense of the Ancients 2 or DotA 2. So just really quickly, for anyone who's not familiar with this game, you play it on this game map. You have 2 teams, the Radiant and the Dire, and they're trying to get to each other's base and destroy the base. And there's these towers, which are represented by these triangles, that will fire at enemy players if they get too close to them. So following the IBA methodology, 2 researchers examined forums, tutorials, and gameplay commentary about DotA, and they developed a list of 24 labels. And that was simplified to 9 labels for the purposes of this paper, and this was that full list. For the purposes of this presentation, I'm only going to talk about 2 of these labels in this demonstration, and that is gank and push. So really quickly again, a gank is when you have 2 opponents playing against each other in a lane, and the ally or the allies of one of those opponents enters the lane from the side to flank the enemy, attack, and hopefully kill them. And then a push is when a player or a group of players really quickly move down a lane very aggressively, usually taking out towers, creeps, and any enemies they find in their way to try and make as much progress towards their goal as possible. So these labels were applied in StratMapper using what you saw, and that was done to 2 randomly selected games from a professional DotA league. The labeling process took about 10 hours, and we calculated an iterator reliability score of 0.72 with 78% agreement, and that was done using Cohen's kappa. After the games were labeled, the player sequences were exported to glyph, and we got this visualization, which you've already seen. So this is the labeled DotA 2 data displayed in glyph, with each sequence in the sequence graph representing an individual player. No 2 players had the same sequence, so they each got their own node in that graph. So specifically, these are all the players based on the team and the game, with the Radiant on the left, the Dire on the right, and then game 1 on top and game 2 on the bottom. So one of the things you might notice is that the sequences for game 1 are very different from each other, while the sequences for game 2 are very similar, which you can tell from how far and close they are from each other. And this is because these games progressed really differently. So game 2 was really back and forth. Both teams had time they spent in a winning and a losing position. In other words, that means that the players in game 2 both played offensively and defensively at different points in the game, regardless of which team they were on. So they had very similar sequences because they had very similar behaviors. Game 1, however, was really one-sided. The Dire team got a really early lead, and the Radiant team never caught up. And this resulted in notably different gameplay behaviors. And then you can see that here, their sequences are much more different from each other than game 2. And this is the game we're going to look at a little bit more, but just really quickly, you might notice that some of the sequences are actually close together between the teams. And those 4 sequences that you see there are actually support players, so they're playing heroes that have supporting skills. And it was interesting to see that they played similarly, despite the fact that their teams were either winning or losing all game. So we can see these behavioral differences a bit more if we look at highlights of the individual sequences. So Batrider and Slark were the top lane heroes from the first game. And if we look at the highlighters in Batrider's sequence, we can see that he never transitioned to the push state, and he also never transitioned from a gank to a kill. I know there's a link there, but I assure you it's going the other way. These indicate more passive and defensive gameplay. Pushing is really risky. You put yourself way out in enemy territory and open yourself up for attack. So if you're in a really disadvantageous position, you're probably not going to do it much. And similarly, if you've fallen behind, killing your opponent's probably going to be a lot more difficult. So a gank can be risky, and even if you go for it, you're probably not going to pursue it to the point of trying to kill them no matter what. So that's what we saw here. Looking at Slark's sequence, we see more offensive behavior. He has numerous transitions to the push state, and he successfully transitions from a gank to a kill. And this offensive behavior implies that Slark was in a more advantageous position that he was able to take advantage of by just continuously threatening his opponent with aggressive behavior, forcing them to stay on the defensive. So this illustrates that IBA can let us see not only the gameplay context, such as who is winning, but how the behaviors and the strategies of players in those winning and losing positions can change because of that context. So wrapping up, IBA is a new methodology that provides a generalizable context-aware means of analyzing game data. It uses 2 visualization systems and a human in the loop to develop labels in context through an iterative process. And this allows designers to better understand how the dynamic environment of their game influences and impacts strategic decision-making. And in turn, this could aid in catching bugs during development or even refining gameplay towards an intended design. Thank you.
Hi, Eric Harpstead, Carnegie Mellon University. Super cool system. I'm wondering to what extent, like, so say I want to apply this to a new game. How much do I need to do? Or how much can I just take your system and it works? Like, do I just need that background map and all of the things go where they go? Or how committed to DotA is it right now? And how much would it need to change to afford a new game?
Yeah, thank you. That's a great question. So the basic part you need to do is like defining the labels for your game, and then just format your game replays into the format for StratMapper. And the rest of the process are automotive. Thank you.
And just to add, we only showed DotA in the presentation, but in the paper we actually talk about a second case study that's on a completely different game. So it is pretty generalizable.
Hello, Juha Ahmad, Tampere University. Thanks for a very cool presentation and your meticulous work. I'm really interested in knowing what kinds of sort of emergent strategies you can think up from just tagging the game in terms of these different kinds of actions. Would there be sort of more latent strategic choices that could be mapped from the data that could be even generalized across games? Thank you.
Yeah, that's a great question. That's sort of like the big question we're kind of exploring with this work. And I definitely, like, we've used this for 2 games, and Glyph has been used for some more, and we've definitely found that you can sort of find similar, like, high-level, general strategic ideas that map across different things. So yeah, that's very much kind of what we're exploring, or at least a part of it. Anything else?
Hi, Eric again. I had a second question. To what extent, and this again might just be, so just a quick clarification, the StratMapper, and Glyph are kind of 2 existing systems that you're pulling together in this, or is one of them new, one of that? That's just a quick yes, no. But.
So Glyph was pre-existing, but we
Cool.
built the StratMapper system.
So to what extent is this system kind of committed to like fundamentally spatialized games, like which space is really important in most games, but in some games you care more about like a topology than you necessarily do about like literal space. And so is there a potential limitation in the kinds of games this could be applied to?
Yeah, I think at present we are mostly focused on 2-dimensional games that have 2-dimensional maps. So yeah, maybe we may explore more like 3D, or if there is no map in a game, that kind of things. Yeah, that we can look for in future.
You still have time? Really need to hold on your email. Don't worry, that's still a weekend planning. Don't worry about the email. So, no questions. Okay.
Thank you.
Thanks.